Namaste. Welcome to this channel, Chemistry Made Easy by Dr. Ashok Mulik. We were discussing the theories of acids and bases, and now we are discussing the relationship between the acids and bases, or the nature of reaction or interaction taking place between the acids and bases on the basis of frontier orbitals. And these frontier orbitals are the providing explanation according to the molecular orbital theory. Here in this point you will see hydrogen bonding, and hydrogen bonding is explained on the basis of these frontier orbitals. So this is according to the molecular orbital theory. Here we see that the frontier molecular orbital approach is most effective to explain why certain substance acts as acid or other acts as a base. So we have seen that the molecular orbital diagrams show the formation of or presence of, we can say, homo and LUMO molecular orbitals. And homos and LUMOs shows interaction of one species with that of the other, and this gives a new product which is showing whether it is stable than the reacting species or not. And depending upon this, we can establish the relation whether the acids and bases react with each other and the resulting species contain the hydrogen bond, whether it is stronger or weaker. So this can be explained here using suitable examples. So acid-base behavior is considered on the basis of this frontier molecular orbital approach. Here we are also going to see that molecular orbital diagram for a symmetric species, that is FHF minus, is generated by combining molecular orbitals of HF and atomic orbitals of F minus. So here you will see in this diagram, so this portion, that is figure 1, will explain symmetrical hydrogen bonding. So we have taken here the example of formation of HF minus. This species can be studied in two ways, that is by reaction between this H plus with 2F minus species, so that will produce FH minus. Similarly, alternatingly, it can be explained by reaction or linear combination between the atomic orbitals of F minus with the molecular orbitals of HF. So both mechanism or both explanation is for formation of this species, that is FH minus. So here if we see in this figure, you will find that the atomic orbitals of the fluorine F minus are shown here. So sigma indicates this PZ. Here you will find that the 2s of fluorine is ignored from this because it is not having any appropriate matching symmetry orbital from this HF. Similarly, this HF has we have shown that the PZ orbital of this F minus from this HF is also ignored or can be ignored because the Px and Py. So you must know that the sigma, this homo of this HF molecule contains sigma. It is sigma in nature, means this is formed by axial overlapping between 1s of hydrogen H plus, or we can say hydrogen 1s, and between PZ of F fluorine. So remaining, that is Px and Py, have pi orientation and they do not have any matching symmetry orbital from H hydrogen atom. So there is no role of these px and py because they are having pi oriented and they do not have matching symmetric orbitals in H plus or hydrogen atom. Therefore, these px and py need not be considered in this MO diagram when we are considering the hydrogen bonding. So we have not shown here the molecular orbitals of HF which are resulting as from px and py and which are non-bonding. So they are not required. So we have excluded them, these orbitals, from this diagram. So we have shown only sigma bonding molecular orbital and this sigma star antibonding molecular orbital. So these are resulting from pz orbital of fluorine and the hydrogen 1s orbital. Then after linear combination, you will find that the resulting molecular orbitals are this of sigma nature, that is sigma bonding molecular orbital of for FHF minus, and this is the another sigma molecular orbital, and this is called the home. So if we see the participating atomic orbitals are this one and these two, that is three atomic orbitals are contributed by one from this F minus and two from this HF. So there are three available molecular orbitals, or we can say atomic orbitals. So they will, after linear combination, they will form three molecular orbitals which are like this. So this is bonding, this is nearly, means it has some bonding characters and some anti-bonding characters, but the bonding characters are smaller and anti-bonding characters are larger. So they are nearly closer to this HOMO, this sigma star molecular orbital. So depending upon the actual energies of these resulting molecular orbitals, the strength of the hydrogen bond produced will vary. So being this symmetric structure, so this is considered as a bonding molecular orbital and this is also bonding molecular orbital. But it has some characters of this sigma, some characters of this anti-bonding molecular orbital. So therefore it is relatively less, it is relatively closer to this sigma star molecular orbital. And therefore we can have the structure here like this. So symmetrical hydrogen bonding in case of FH minus is observed. Later on we will see another molecular orbital, that is here you will find unsymmetrical hydrogen bonding. So we are generalizing the species as BHA, that is boron, hydrogen and A is any other species. Here A can be, here we have seen this A, this is A, that is FON. So here we can have this A as F, similarly oxygen and nitrogen, which are more electronegative. So we can also consider any other less electronegative atoms also, but depending upon the magnitude of electronegativity, whether it is greater or smaller, the strength of the hydrogen bond will vary. When we are using this A as F or that is fluorine or oxygen or nitrogen, the strength of the hydrogen bond will be stronger. But if we use less electronegative atoms here as A, then the strength of the hydrogen bond produced will be relatively weaker. So this can be understood by using these some diagrams and this equation. So here B, that is boron, reacts with HA, gives BHA. So depending upon the strength of HA means the polarity, or we can say electronegative characters of A, this stability of the species will vary. So we will explain it later. Greater the loading of energy of the BHA orbital, stronger the hydrogen bond formed. So this can be, with this equation or formation of BHA can be considered like this. So this is the another diagram, that is figure 2. So you will find that boron has this sigma molecular orbital, that is PZ atomic orbital having electron pair. So this can be considered as HOMO for boron, and the higher orbital is HUMO. Similarly here it is HOMO for temperature minus and HUMO which is vacant. Here the boron atomic orbitals are shown here, HA molecular orbitals are shown here. So this is the molecular orbital of sigma nature, and this is the molecular orbital of sigma star, that is antibonding and bonding. So this is called a HOMO, this is called a HOMO, this is also called a HOMO, but this is HOMO for HA and this is HUMO for HA. So HA will have this HOMO and this HUMO. Similarly BHA will have this HOMO and this HUMO. Similarly boron will have this HOMO. So when they undergo linear combination, they will show that this sigma type of molecular orbital, atomic orbital will undergo linear combination with this bonding, that is HOMO molecular orbital of HA, and they will show this type of electron distribution, or we can say the orientation of electron clouds. So here electron pair of this sigma of HA goes into this low energy bonding molecular orbital, and this sigma has electron pair which moves into this sigma, the molecular orbital called a HOMO, contains this electron pair. So this electron pair is moving from this boron sigma, that is HOMO, to this HOMO, and it is also reacting with this sigma of HA. So this is contributed by three species, that is this sigma bonding and this antibonding molecular orbitals. But this is contributed by this sigma of HA and this sigma of boron, whereas this antibonding molecular orbital is contributed by this sigma and this antibonding molecular orbital of sigma nature. So in this way we get this stable structure and shows stable hydrogen bonding. Now this type of structure can be generalized, or we can say that is we can vary the electronegativity of A, and we can understand later which diagram is suitable for this type of structure. So we can consider this first, where the diagram is of similar nature but there is slight variation you will notice here. So if we consider this type of reaction, or this reaction can be considered in three types, means the products are considered of three types. So this is one possibility of formation of BHA. So in this case you will find that the energy of this HOMO of HA is lower than the HOMO of this boron. This is important thing, that this HOMO of HA and this HOMO of boron are showing that the HOMO of HA is much lower in energy than this HOMO of boron, and because of this, after linear combination between these two pairs, there is formation of a BHA bond pair. This is bond pair, that is bonding electron pair on molecular orbital. Similarly, this bonding molecular orbital may show this. So you will see here this is bonding, this is HOMO and this is LUMO for HA. But here you will find that the LUMO is higher energy than this HOMO. This HOMO is higher energy than this HOMO of boron. So you will find here that the HOMO of product BHA is higher energy than the HOMO of boron. So here you will find that the reactant have HOMO of lower energy and product has HOMO of higher energy. So in this case you will understand that the stability is always for low energy state. So this is low energy state, means boron is stable, so it will not react with this HOMO, means HA. So you will not get the suitable product. So that is poor interaction. So the higher energy level of this BHA do not show favorable condition for formation of BHA because this low HOMO is lower energy than this. So this is important. So this figure A shows that in this possibility the formation of BHA is not suitable or not possible. Then you will see in another figure B. So here you will find that the boron has this HOMO and this HA. So this part is of another diagram. So this HA has HOMO and this HA has energy much lower than this HOMO of HA. Similarly, this HOMO and this HOMO are separated by a large energy difference. So after a linear combination between them, there is formation of HOMO for BHA. So it is the energy of this BHA HOMO is lying much below compared to this. You can compare this HOMO and this HOMO. This is higher energy than HOMO of boron. This is much lower energy than HOMO of this BHA. So this gives better stability to the formation of BHA. So this HA is very like to this BHA and it is mainly contributed by this HA HOMO and less contributed by this HOMO of boron. So this is more possibility. This use the structure or diagram for explaining the more stable structure for the formation of BHA. So this diagram, that is big diagram, is suitable to explain the correct behavior of this structure or spacing. Now the third case, C. So here you will find that this boron HOMO and this boron HOMO. So we can also mention here that these are the HOMOs. This is HOMO. So the HOMO of boron and this HOMO of A or HA. You can consider this HOMO of this boron and HOMO of this HA or A minus are relatively at higher energy. So this does not provide suitable condition for undergoing linear combination. So this shows that this type of formation will not be possible. Similarly, you will find that this HOMO A has HOMO much higher energy. So that is obtained or can be obtained from this HAU. But that is being much higher, it is not useful condition. So this HOMO is higher level than the HOMO of this HA. So this is also not giving suitable condition. So this is the HOMO. So you will see that this HOMO is higher energy than this HOMO. So therefore this condition, this figure C, shows that the formation of BHA is not possible here. Now if we see the structure like this, then BHA, here you will find that the simplified structure of BHA. So the molecular BHA is like BHA, where there is angular molecule. So hydrogen is at the center, as you have seen here. Hydrogen is at the center. It is less contributed by boron and more contributed by HA. So here the hydrogen bonding between, that is HA bonding, is more possible here also. So here you will see that the distance between, or this angle theta, so this is 180 degrees angle, and this 180 to this means 0 to this oxygen is theta, and this theta is 10 to 15 degrees. So such type of formation of angular molecular species is possible, where this molecule or bond is 3 centered or 4 electron bond. So there are 3 centers and the electrons involved are 4. As you know that these are 4 electrons involved here in the bond formation. So this is called 3 centered or 4 electron bond. So here hydrogen bonding, you will see here that if A is like fluorine, oxygen, nitrogen. So if you consider A is fluorine, oxygen, nitrogen, then what will happen? You can consider this oxygen. So it is more electronegative. So that will attract a more electron cloud of this HO, so that this BH species becomes electropositive, the electron deficient. This is electron rich, and because of this, the electron of this H plus is nearly transferred to this oxygen. So electron is, because electron density is moving much away from oxygen, and it is nearly transferred to oxygen. So this bond has less existence, and therefore the electron density plays very important role. So it means the species should be relatively less stronger, or in other words we can see, if this type of oxygen is A, means it, the strength of the bond, that is oxygen or nitrogen or fluorine, shows that if the electronegative nature of this A is more, if the electronegative nature of this oxygen is more. Now this is compared here, you will see that greater the loading of energy, BHA orbital stronger with the bond. So you will find here, you can assume this structure or this structure. So if it is HA, so you will find that if these two molecular orbitals are lower comparatively from this energy level, so greater the difference between these energies, stronger is the hydrogen bond. So you can consider. Similarly, lowering of this energy and this molecular orbital shows that stronger is the HA bond. So if another way, alternatively, you see that if this molecular orbital is at this level, HA is here, or any other species, then you must understand that this hydrogen bond is weaker. So as the energy difference between these two is low or less, the strength of the bond, hydrogen bond, is less, means the bond is weaker. And if the energy difference between these two is larger and larger, the strength of the bond is greater and greater. So this MO diagram or BHA or this FH explains how the strength of the hydrogen bond varies, or where the bond is stronger or weaker. So with this we will stop our discussion. Thank you very much for watching this video. Please subscribe to this channel and please press bell icon and like button. Thank you very much.